Could we even find von Neumann probes in the solar system? Do we finally have an explanation for little red dots? Could alien megastructures be raining down on the moon? All this and more in this week's Space Bites. If you've watched my channel for any length of time, you know that I am very compelled by the Fermi paradox, and specifically, I am really interested in the Hart-Tipler conjecture. And this is this idea that it's not about us looking for aliens out there across the universe, trying to detect signals, that it's about any advanced civilization building self-replicating robot probes and then spreading across the entire galaxy. We don't need to be looking out across the cosmos. We should be wondering, why isn't the solar system filled with von Neumann probes, with self-replicating robots? Isn't that the kind of thing that we should be able to detect? Well, according to a new paper, the answer is probably not. That our ability to explore the solar system is pretty terrible compared to what we would need to be able to comprehensively say we have searched the solar system. So I'll give you a couple of examples. For the Earth, obviously, we have mapped and scanned Earth to a pretty high degree. But yet, of course, people are detecting what they think are UAPs with their cell phone cameras and military instruments and things like that. And so there's still things at the limits of what our detection ability is. You think about how comprehensive our scanning of the Earth is. It's not great. The moon, we have scanned the surface of the moon down to features as small as about a meter. We've done very similar things on Mars. But for the rest of the solar system, we really can't see anything. Recently, astronomers have been able to resolve features on, say, Saturn's moons with the biggest telescopes that we've ever built down to about a kilometer. And so would a self-replicating robot probe be smaller than a kilometer across? Probably. And so if it's out in the Kuiper Belt, or if it's out in the Oort cloud, or on any of the moons across the solar system, we probably don't have the capability to find it. But it's worse than that. I mean, obviously, these things were in orbit around the Earth. We would detect them. But let's say that they did go to the moon a long time ago, maybe set up some kind of robot factory on the surface of the moon. Well, the constant weathering on the moon and Mars from micrometeorites slamming down onto the surface of the moon would kind of wear down and make any object buried under the regolith. And so we wouldn't even recognize it if it was there on the moon, unless it had landed fairly recently. And so, according to the paper, we really have only just gotten started in searching the solar system for evidence. And that is probably the most productive way that we can find evidence of any kind of extraterrestrial civilization in the universe. That if it is true that advanced civilizations send out probes to other worlds, then if we search around in the solar system, much better, with sending small probes to asteroids, scanning the surfaces of Europa and Enceladus, and really interesting places where there are resources in the solar system, that might be very productive for us as a sort of top priority. Anyway, if you're interested in this argument, we've got a story from this by Andy Thomaswick. Well, let's say that we do want to continue searching the cosmos for evidence of advanced civilizations. And, the traditional version of this is SETI, the Search for Extraterrestrial Intelligence. And in general, you're listening to radio signals from other civilizations. And that's a very good idea, because when you think about the kinds of natural signals that are out there, radio signals from an intelligent species would be dramatically different. There are things that we can transmit with radio that just natural things can't do, wouldn't do. Repeating prime numbers, different frequencies, like it just doesn't exist in the natural world. And so you get this unambiguous signal. But searching for someone trying to communicate with us is kind of a long shot. The other idea is that we want to search for indirect, passive evidence of advanced civilizations. Imagine someone detecting the chlorofluorocarbons in the atmosphere of Earth, or the radio transmission from our air traffic control system. And so in a new paper, researchers looked at what are the kinds of passive technosignatures that could be out there. You can imagine, if something is a cloud of material that is moving in front of the star, we would detect this diffusion of the light coming through the star. Maybe if it's actually occulting, blocking the light from the star or the planet, maybe that's something you would see. Or like something that is glinting, say there's a mirror that is reflecting sunlight and we happen to catch it at the right angle, we would see this glint. And so you kind of imagining this future of megastructures, very large objects that advanced civilizations will build to assist in their technology. But civilizations are probably short-lived, that maybe they'll be around for 1,000,000 years, and then for some reason they will run out of steam and they will leave behind their artifacts. And the artifacts are only going to be kept in place by constant propulsion, maintenance, things like that. And without the civilization there to maintain it, all of this stuff is going to start to wear down and break down. And so in this paper, the researchers propose that you're going to get, say, like if you had a Dyson sphere or large space stations or whatever, that this stuff is going to crash into each other. It's going to grind up. It's going to turn into dust, but a very special kind of dust, like high-tech dust. And that this stuff will be very light, pushed out of the star system where it began, and then will be transmitted through the interstellar medium to other star systems, like the solar system. And then this would rain down on, say, the moon. And so when we go to the moon, we're going to be doing sort of geological core samples, looking at the history of the surface of the moon. But the researchers say that one of the things that we should look for is evidence, like grains of dust, where their chemical structure, their metallurgy is something that can just not be explained by natural processes. And on the moon, you could have a surface that is over 4 billion years old. You could core down and look back through just hundreds and hundreds of millions of years of history of the Milky Way. And so if at some point in a distant star system, a Dyson sphere ground itself up into sand, we might see the evidence on the moon. We've got a story about this from Andy Thomaswick. So exoplanets are weird. Or like maybe we're the weird ones, but we're definitely building this much larger catalog of the kinds of possible exoplanets are out there. And, we have examples like hot Jupiters, where you've got planets that are orbiting around the star in just a couple of days. We don't have any of those in the solar system, or super Earths. And one of the other kinds that we have are called sub-Neptunes. And so these are somewhere in between a super Earth, which we don't have, and the ice giant planets like Uranus and Neptune. And so they are large, they are more dense than a gas giant, but they are less dense than a terrestrial planet. And the assumption, and in fact, a lot of the evidence is building up, that these have a lot of methane in their atmosphere. And so astronomers are proposing that there is a class of sub-Neptunes at just the right temperature where we should be able to detect polycyclic aromatic hydrocarbons. And at that term, like PAH, if you don't know what that is, the sort of general definition is soot. So think about, say you've got a barbecue and you've got this stuff that's on the barbecue afterwards, it's like black and kind of sticky. Those are PAH. And so under certain conditions, when the temperature range of the exoplanet is around 227 to 527 Celsius, so pretty warm, then you're going to get this chemical cycle in the atmosphere of the exoplanet, where various chemicals like methane and others are mixed and matched, and you're going to get it turned into this soot, which is then going to rise up in the atmosphere, and we should be able to detect it. And this is very interesting because, we think about the kinds of precursor chemicals that were found on Earth that helped lead to the formation of life on Earth. We see this in other places around the solar system, in meteorites, we see them in giant star-forming clouds, and now we might see these in exoplanets. We've got a story about this from Lawrence Tugnetti. So we've talked about the mystery of little red dots for quite a while now. And if you sort of need to be brought up to speed, when James Webb first became operational, one of the interesting objects that it detected was this whole class of things called little red dots. And we don't have anything like this in the modern universe. So whatever this was during a phase of the early universe. You had these very tight point-sized objects. Like these things are not much bigger than, say, a solar system. And yet they're pumping out a lot of energy, but that energy is shifted off into the red. They're a very warm infrared source. And one of the first explanations, like how would you get something that is so bright seen early on in the universe, is a supermassive black hole. If it's extreme, black holes are probably involved in it somehow. But when you observe actively feeding supermassive black holes, you also get a lot of X-ray radiation. These things have this giant accretion disk around them. It gets very hot, pumps out a lot of radiation. And the weird thing about the little red dots is you saw the bright light, but you didn't see the X-rays. And so now astronomers have used James Webb for a long time and think they have revealed what's going on. So they were able to observe an object called Glimpse 17775. And this is a little red dot that is behind a much closer galaxy cluster. And the galaxy cluster is acting like a natural telescope lens so that James Webb can magnify and multiply its time on the object. So they're able to get 30 hours of it observing this one little red dot. But because it was going through this gravitational lens, it was the equivalent of James Webb working for 80 hours. And what they found is that you've got this large accumulation of dust around this object. And the story that they're starting to piece together is you do have a supermassive black hole, an actively feeding supermassive black hole. It's probably pumping out all of that X-ray radiation, but then it is surrounded by so much dust that the dust is absorbing these higher wavelengths of radiation and then retransmitting them in the red, essentially washing out all of that high level radiation. And so this is a very strong indication that the explanation for little red dots is supermassive black holes shrouded in huge envelopes of dust. So if true, I think we're getting to the point where the mystery of little red dots is almost solved. We've got a story about this from Mark Thompson. The European Space Agency is working on its next generation gravitational wave observatory. And this is going to be a space-based gravitational wave observatory called LISA, the Laser Interferometer Space Antenna. This will be a formation of 3 satellites that are sending lasers at each other. And inside each one of these satellites, there's this test mass. And it's able to measure the movements of this test mass to picometer resolution. And so this configuration will allow LISA to detect the mergers of supermassive black holes, something that is beyond the capability of all of the ground-based gravitational wave observatories that we have today. And it's funny. So one of the issues, one of the concerns that the researchers said as a sort of a source of noise in the system is that masses moving relatively close to LISA could actually cause it problems. An asteroid comes too close, then its gravity will affect the test masses inside the satellites, and that could distort its results. And so a lot of time and energy has been spent to try and get that noise out of the system. And so a new paper said, actually, we could use that as a feature that when we detect this gravity that is affecting the test masses, we could actually characterize the mass of the asteroid as it's moving by. And we actually don't have a lot of good information on the masses of asteroids. We've only close up observed and gone into orbit around just a couple. So in theory, LISA might detect about 3 of these asteroids and be able to categorize their mass very closely. And you kind of know that an asteroid came very close to the constellation. So, 3 doesn't sound like much, but it's 3 more than what we already have. We've got a story about this from Andy Tomasuk. If you want to learn more information about LISA, I talked to the designer, really, of the experiment, Dr. Stefano Vitale, and I think you will find it an absolutely fascinating interview. Every week we do a vote on our channel where you tell us what you thought was the best space news story of the week. And the winner last week was evidence for an ancient planet in the solar system. So thank you everybody who voted last week. Now, when you're watching this episode, we have already put the poll for this week's stories into the post tab here on our YouTube channel. You should just see it while you were scrolling on YouTube. But if you don't see it, then go into the post tab, vote on a whole bunch of the stories, and that should have the algorithm start showing these to you. Of course, you should also subscribe to the channel, like this video, click on the notifications bell. You got to train the algorithm or be trained by it. And speaking of LISA, its original purpose, it's not to find asteroids. Its job is to detect merging supermassive black holes. And a new paper shows that, in fact, there is a bit of a problem that we need to be careful about when analyzing the results from LISA. And that is because LISA is part of the solar system, and the solar system is part of the Milky Way. And the Milky Way is filled with mass, and it has an orientation. And so as gravitational wave events are happening out there across the universe, as the gravitational waves are making their way to us, they're going to be passing through the Milky Way in different slices. So you can imagine if the Milky Way is face on to the gravitational wave, we'll see it in one way. If it's coming in edge on, then if it's on the far side versus the near side, it's going to be different. And according to this new paper, that will actually distort the results and actually make it a little more difficult to be able to detect where that gravitational wave event came in. And so there's going to be some work to be done to try and remove that noise from the system. But the really interesting side effect of this is that we will get an independent measurement of the mass of the Milky Way. And there are like 10 different ways that people have tried to measure the mass of the Milky Way, and the numbers diverge in some cases quite a bit. You know, they're very large error bars. And so now, just by trying to find gravitational waves across the universe, we might also figure out the mass of the Milky Way. Got a story about this from Mark Thompson. Pulsars are a type of neutron star. So when you have a star that is more massive than the sun, it dies as a supernova, explodes, you get the remnant, that is a neutron star. And when they're fresh, they are often spinning very rapidly. It can be spinning hundreds and hundreds of times a second. And we know of hundreds of these pulsars, and they're wonderful. I mean, they are these natural ways that astronomers use to measure all kinds of phenomena in the universe. Part of the problem is that many of the most useful pulsars can be on eccentric orbits around some kind of binary companion. But now astronomers have found what appears to be the most circular orbit for a pulsar ever found. The pulsar is called PSR J1810 0623. And it was found by the Chinese FAST telescope. This is this 500-meter radio telescope in China. And the astronomers know that this pulsar is orbiting around a companion star, and that they are orbiting a common center of gravity, and that the eccentricity of the pulsar is 0.000015. So it's almost a perfect circle. And this is great, because now astronomers can use this as a way to test various theories about gravity, relativity. A lot of big tests in the universe about the laws of physics somehow involve pulsars, and this is one of the most pristine, useful pulsars ever found. Essentially, you've got this perfect circle, and that allows you to remove the variable of its eccentricity. I've got a story about this from Mark Thompson. Venus has a very unusual rotation. When you look from above and you look at the rotation of all of the planets in the solar system, they are all rotating in one direction except for Venus. It is flipped upside down, almost perfectly upside down, and so it is rotating exactly backwards from the rest of the planets in the solar system. How did this happen? There have been a range of ideas that have been proposed, that maybe because Venus never had a moon, it didn't have the stability that the moon gives us. Maybe it did have a moon, and the moon crashed into Venus and rolled it over. Or maybe just as part of the early migration in the solar system, the gravitational interactions with Earth and Mercury, that rolled it over. Well, now a new paper has done a bunch of simulations of giant impacts on Venus, to try and figure out what kind of impactor would produce this. And they found that if you got an impactor that had about 1/10 the mass of Venus, and it hit at a very high angle, that it would slow down the rotation of Venus, so it would actually become more unstable in its rotation, allowing it to slowly flip itself upside down. So hopefully this will give the various space agencies more incentive to go back to Venus. There's a couple of missions that are in the works right now, and you can imagine if we could find evidence of some giant ancient collision on Venus. But we need better maps of the surface of Venus. So this is just like more reason to go back to Venus. We've got a story about this from Bruce Dorney. And of course, this is just a fraction of all of the stories that we're covering on Universe Today. We often do 30, 40, sometimes upwards of 50 stories on Universe Today about space and astronomy and space exploration and all kinds of really cool stories. And if you want like a nice summary of everything that we're doing, you might want to sign up to my weekly email newsletter. I write it by hand, covers all the stories that we're talking about. It's completely free. Go to university.com/newsletter to sign up. I'm going to talk about YouTube thumbnails, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailout, Dark Finger, David Gilton, and David Matz. Enthrall Reading and Math for Toddlers, Eric Lindstrom, Evan.pro, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Sitz, Michael Purcell, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick69 and 4, Ring Kaidu, Richard Williams, Sean Sargent, Stephen Fallon Team 49, Telescopes Canada, Vlad Sheplin, Wolfgang Klotz, and Zelda Board Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. I got this comment on YouTube, Rev9759. What an odd choice of a thumbnail. Why did you include yourself? Now, if you've spent any time on YouTube, you are probably familiar with the language of YouTube thumbnails. Mr. Beast is right at the very forefront of making the most effective clickable thumbnails that you possibly can. And the thing that YouTubers have figured out is that if you put a face on a thumbnail, that will often draw the eye and is more compelling. And we actually have kind of a bit of a language in the way we do our thumbnails right now today anyway, which is that if it's Space Bites, which is the thing that we record and release on Fridays, then it will have my face. And so this is me reacting to the news of the week. And I'm, got some kind of hilarious overreaction that Anton, my editor, has pulled out just the derpiest frame that he can from the video just so he can add that to the video. And I have no control over this whatsoever. And the reality is that it works. And we live in this world now where there is so much faceless AI slop videos on YouTube that people need some way to be able to distinguish between something that is just, robot voice, space stuff to fall asleep to versus this is a human being, a space journalist who knows what they're talking about, has been doing this for a long time, and is going to give me some useful news. And that is a way that we try to provide some kind of indication that this is the real deal. This is actually me. Now, obviously, people can fake my image on there, but I'm not that popular yet. So this is sort of the path that we go. And then when we do the QAs and the interviews, we often don't put my face on the thumbnail. It's just that way to be able to distinguish between the two. But the reality is that it works. That if you put a face on the thumbnail, if you put a big red question mark, if you have an ambiguous title, like there are all of these things that you can put on the thumbnail and in the title of your video that draws people in. There are some great videos that go into the science of this. Veritasium went and just did an incredible deep dive into the science and really kind of the game theory reasons why you have to, if you want to be on YouTube, you want people to watch your videos, you have to play the game. And so we play the game. Now, the line that we draw is that we want to make sure that we are providing factual information in our videos, that you may feel compelled to click the link to the video, but what you're going to find inside the video is as good or better than the reason that you were clicking. Now, obviously, sometimes that's going to backfire. People are going to get really mad at us and they're going to accuse us of being clickbait. That's just, part of the game. But the underlying it all, our job is to give you the best possible space science news reporting that we can at a ferocious rate, and hopefully be a place that you can trust what we're talking about and what we're saying, and that you can recognize when this stuff is coming from us versus something that is just generic. So I hope that explains it. So I don't like to see my face on YouTube thumbnails at all. And yet I put up with it because I know that it's effective. All right, we'll see you next week.